Hello everyone, it's July the 8th. Alright, let's get into it. Nothing of concern. Alright, let's take a look. Maximum length of repeated subarray. Repeated subarray. Another question about array. I don't think I'm pretty good. I don't think I'm very good at arrays. Always give me trouble. Given two integer arrays, nums 1, nums 2, return the maximum length of a subarray that appears in both arrays. So 3 to 1, right? 3 to 1. And 1000, 1000, looking to be O(n) squared-ish. And 0 to 100. We have a hint. Alright, so we want is the maximum subarray. So let's take a look. Subarray, something to keep in mind is, looks to be dynamic programming, right? And we can say maximum subarray, and it has to be the same size, right? Which means at any position, right? At any position, and then we have a length. So let's say basically the problem is if we know, let's say, ending in a certain position, a certain length, right? And then if I know, right, given a position, so it has to be, that doesn't have to be the same position. Given two positions, right? Given two positions, when the value is the same, then we have the likelihood for them to match. So right, if the two values are the same, then we're going to check. Right, we're going to check whether this is a matching subarray. So we look to the one ahead of it, before it. Right, we'll look for one before it and see if see what. So at a position is the longest matching, right? So the longest matching repeated subarray at each position, right? So as we go through, we can try it. So let's say the columns are, what are rows and columns? Well, it's one array and then the other array. So like the longest matching of these two, So yeah, maybe this one works. So it's gonna be a n by n, right? So it's 5. So we'll do 5, 2, 3, 4. 1, 2, 3, 4. Right? So we have 1, 2, 3, 2, 1. And this one will be 3, 2, 1, 4, 7. So the first row, so each position is the longest repeated subarray that happened in both, and I would take the size. So at the beginning, it's going to be 1, 2, 3, 0, 0, 1, 0, 0, right? And we also can do the first column. It's going to be 0, 0, 1, 0, 0, right? Now look at the second. So we have 2 and 2, right? So we'll take a look at this one, 2 and 2. So we say 2 and 2, they match, right? So we look for the one before. So look for the one before, and before we have 0. So 2 and 2 is going to be 1. And 2 and 3, so ending in this, that's going to be 0, right? So which means if we're looking at this position, we want to see the longest that can match. That's going to be 0. And 2 and 2 again. So now we're looking at 3, 2, and then 3, 2. So we look for above, and so that's 1. So 1 plus 1 is being 2. This can be 0. So 1. So everything that's not the same is going to be 0, and this one is going to be 3. Everything's not the same is going to be 0. Everything not the same is going to be 0, and then we look for the maximum value, right? That shall be it. That shall be it. Should be and then I think this can be done in one, like on extra space. Yeah, so basically we just say, right, if they're the same, yeah, if we loop through both, right, if they're the same, then we have a possibility to look at above, which is actually the value in front. No, not actually the value in front. So we do have to use, let's try it. It's going to be on squared, which actually I'm not sure it's going to be passing or not. On squared, but the 1000. All right. So let's take a look. All right, so we're gonna have, what are we gonna have? We're gonna go through every one in the first and go through every one in the second. And we're gonna have a result is going to be called a 0, right? And we're gonna have a dp is going to be a 0 times let's do like one more. So let's say also the lengths are not the same, which is fine. So we can say n1, n2 equals to the len nums1 and len nums2, right? So the dp, we just pick one. Let's call it nums1, right? So we're going to say n1 plus 1, right? We're going to plus 1. And then we're going to say for I in range, that's the row, it could be n2, right? And for j in range, n1, right? Before we do that, we're going to say a temp is equal to this, right? Times n1 plus 1. All right, so now for each one, we're going to just compare, right? We're going to say if nums2 j, I mentioned nums1, so we put this as n1. So nums1j is equal to nums2I. Hold on. I don't like it. I do not like it. I like I to be associated with 1. But I is also the row. So, that's fine. And 2I then. So if these two are the same, then we say dp, and remember, the dp that we're doing is going to be 1 larger. Alright? So it's actually not dp, it's temp. It's going to be 1 larger. So 1 larger, actually it doesn't matter about I, it's just j. So it's going to be j plus 1, right? It have to be j plus 1. Well, equal to dp j, right? dp j, because that's the previous one. dp j plus 1, right? So if they're equal, that's going to be this. If they're not equal, that's a 0, right? That's a 0. So we go through this and just need to keep track on the largest value. So if they're equal, then we can compare. So we say res equals max res and temp j plus 1, right? And once we're done with this, dp gonna equal to temp. And then we'll go back again, and then after that we return the res. Okay, so give this, we have two test cases. The first one's 1, 2, 3, 2, 1, paired with 3, 2, 1, 4, 7. This one gives us 3. Second one is both are zeros. So 0, 0, 0, 0, 0. So 5 zeros, 5 zeros again, and give us 5. And I like there's a test empty, and it doesn't matter. That should give us 0, right? Okay, so we have nums 1, nums 2, and this is find length nums 1, nums 2. Run it. Num2 is not defined because it's not num2, it's nums2. Alright, we pass 3 test cases. I try to run it. Pending. Judging. Oh, Lord. It was so slow. When my hit like 5% ranking, something like that. Oh, it's not too bad. Oh, but they're very fast options. Okay, so this is a 1D array DP solution ON squared, which runs at 3,156 milliseconds. It's understandable because it's the input size is huge. Yeah, it's huge. Now we can definitely optimize, right? Because at each one, I'm comparing with the same value, right? So if, like in this case, 4 and 7 is going to generate like nothing, right? It's going to generate nothing. So doesn't really, therefore, if you think about it, what we care about, right? What we care about is all the ones that do match, right? Which means if there's something that don't match, we don't care. We don't care if it's not matching. So if I can get the, and also keep in mind, this is a 100, right? There's only a 100. If this is only value 100, I mean, what if I obtain the indices of everything? I mean, we still think in terms, right? In terms of dynamic programming, but instead of looping, right? Instead of looping, what if I can go directly? Like if I have 1, 2, 3, 2, 1, and then now my value to compare is 3. So I look into it and I immediately find that 3 has index 2, right? 3 has index 2. And then I just update that one immediately. That is a very good thinking. And if we have repeats, like 2, we have repeats, so we just go with the repeats, right? We don't have to check any value that is not inside. So let's try that idea. So we just need to create, we just need to create a mapping, right? So we're gonna say, let's create a mapping for num1. So nums1 map is equal to a dictionary for I, n, in, enumerate nums1, and we're gonna say, ooh, no, we're gonna place this into a list. So no. I think we need a default dict. From collections, import default dict, right? I think default dict is what we need. So I think this one, change that into default dict with a list. right? And then for I and in enumerate nums1, and we basically say nums1 map and dot append I, right? So we have a mapping. And then same thing, rest is 0, and do we want the nums? Yes, we do want the nums, right? We do want the nums. So we go here, copy the entire thing. We go down here, paste it here, right? So that's what we have. Then what? Then we're gonna do the same thing, right? Yeah, we have to have dp as well. dp is gonna be 0 times num1 plus 1. It's the same thing. For I in range n2. Okay, so for the row, oh, we got it wrong. N2, it has to be N2. My bad, it has to be N2. It's not N1 mapping, it's N2 map. So it's N2 map. So N2 is map because, oh, wait, which one do we want to map? No, it's N1. Hold on, N1 is mapping. N1 is map, and at each row is N2, right? So this is N2, and we compared N2 to N1. Yes, that's right. So N2, and we don't have to go J anymore. So this is N2, right? And what we do is we probably don't even need. Okay, just say like N in nums2, right? Yeah, just say N in nums2, and then we say, what do we say? We say temp, right? Temp will do the same thing, 0 times n1 plus 1, and for j, right, in nums1 map, nums1 map what? N, right? For nums1 map, that is all the indices, right? All the indices. So when we get this, we say temp j plus 1 equals dp j plus 1, and res equals max res temp j plus 1, and when we end, dp equals temp. Right, so this is the same. The only thing difference is we don't need this one either. We just need n1. We don't need n2. Right, we only need n1. And we make it cheeky, so we can do here land nums1. Save a line. Yeah. And then return the rest. Alright, let's say this one pass as well. So I think this one, which means if n, right, if n is not a nums map, then we're just gonna skip it. Right, we're gonna skip it. So I think it's still O(n squared, right? It's still O(n squared, but I think it'll be faster because we're skipping, right? There are cases we're skipping. Like a best case scenario, this will be O(n). Right? Best case scenario is will be O(n). Worst case scenario, actually, worst case scenario is O(n squared. Like if both are exactly the same, so everyone will have to go through everything. But the best case scenario will be O(n). Average, average probably still O(n squared, but we'll try. Right, we try. See if this one is any faster. Pending, judging. Nah, I don't think so. I think it's the same performance. Yeah, I don't think it's any faster. All right, so the best solution might have something different. Pre-build a mapping for num1 to speed things up, but overall runtime is the same as solution 1. All right, let's take a look. What do we have? The good solutions. All right, this is a medium question, so not too hard, all right, compared to yesterday. Yesterday is not hard. Yesterday we just I got stuck, and I solved it, but I got stuck halfway through. All right, brute force with initial character map. J is this if this. N times n. Binary search with naive check. There's a binary search in this. Ooh, what the hell? It's a binary search. K subarray common, and there is a length j. Hold on. If there is a length k subarray common, then there is a length j subarray as well. I check length to be the answer to the question. Is there a subarray with length common? That is the same idea as what we had yesterday, right? So, oh, and then it's just trying to push it up to the right side. The range that must take the form at least one true, we can binary search on this function. Is there a subarray with length common to A and B? Invariably check high, always be false. So we'll start with high is min plus 1. Clearly check high is false. Now perform a check in the midpoint when it's possible. Then low is mid plus 1 because we want to push to the right side. When it isn't, high equals mid, yes. At the end of binary search, high equals low, and the low is the lowest value such that check low is false. So we want low minus 1. Hold on. So this saying when I check, right? When I check on the mid, if it's true, then we want move, right? If it's false, then we move here. If it's true, so we're always trying to move up. And yeah, and then when we come out, it's going to be false because the only thing we move is this. It's going to move up, right? So eventually, when they're the same, the only possibility that they're the same is when low plus 1, right? And that means to do low plus 1 is going to be true, so we have to do low minus 1. So we can check I and I plus k using set structure. So, oh my god, I think this is minus length plus 1. We get all of this, right? And then get all of this. So ending this, oh my god, this doesn't look fast at all. This is a time limit, right? Dynamic programming. Yeah, I think this is the same. Binary search with rolling hash. Ooh, interesting idea. I don't know what rolling hash is. This is OMN. I said ON squared. That is not right. MN, come on. These two things are different length. MN. Ah, in that case, I do think, no. I just make things more complicated. N1 times N2. Yeah, we know. Alright, rolling hash. Oh my god, so long. But this one's so fast. M plus N times log minimum MN. I cannot understand approach 4. Oh, there's an OMN sliding window. I want to take a look. Approach 2. Ah, they're using strings. So we turn those into string and we use this to check. Let's use this to check. Oh, interesting idea. A very interesting idea. Oh, but this is mapping to a character. Ah, yeah, it works because it's 100, right? Only the value is 100, so we can use this to represent. I want to try that. I want to try that. This one is interesting. All right, so let's take a look at this one. Binary search with rolling hash. Or do you want to? I want to code. Let's code the Pacman's idea. Yeah, I want to try that. Interesting. Very, very interesting. So, courtesy to Mr. Pacman. I can also. I don't think I can copy his share. I can do. Copy the link. So this is the binary search solution suggested by the official solution. However, Mr. Pacman tweaked it such that we build strings for comparison instead of tuples. The fact that the values in the arrays are smaller, are between 0 and 100, allows us to transform each number, each value, to an ASCII character. Yep, so what we're going to do is we're going to def a check, right? We're going to check. What do we check? So we check on length, right? We check on length. So basically, what we're saying is we're going to create a set. Yeah, so before we do that, when you redo, we say str1 equals dot join join what? join character n for n in nums1, and we'll do the same thing, right, for string 2. And now we have 2 strings. Now we're just going to do all possibilities, right? So set1 equals set what? For I in range len str1, right? Len str1 minus length. So I minus length. Say that's 3. I want 2. 3 minus 2 is 1. So 1. I can only go 0. 0 plus 2. 0, 1, 2. What's the end? So it's like 3, 2, it should be n of 1, right? N of 1. So it's 3 minus 2. That's 1. But we want end at 1, right? We end at 1, which means if we end at 1, this has to plus 1, right? 3 minus 2 is 1 plus 1 is 2. So they end at 1. So every 1 is going to be str1 I to I plus length, right? So I is 0, 1, I is 1. 1 plus length, length is 2, so 1 plus 2 is 3. So we don't do 3, but we do 1 to 2, right? That's it. So there's going to be a set for this, and we're going to return any, any. Actually, we're going to say set1, set2. So there's going to be set2 and str2, do str2, right? And then we're going to say any s2 in set1 for s2 in set2, right? So let's check. And then binary search low high equal to 0 and to be the minimum, len str1 len str2, right? So that's the starting point. Minus 1, but plus 1. Why do we plus 1? Because if it's that value, then we'll never reach it. So we have to go plus 1, right? Because the thing is, while low is smaller than high, right? That's our goal. Mid equals low plus high divided by 2, right? And then we say if check mid is true, right? If check mid is true, that means we have to keep pushing. So low needs to equal to mid plus 1, right? It's a mid plus 1. Because if we don't do this, right, then it's actually fine. I don't think I need a plus 1. I think this one shall be fine. Yeah, because low would be mid plus 1. And, oh, hold on. Low is mid plus 1. Mid plus 1. And mid plus 1. And then we will exit already. Right? If low is mid plus 1, and then they're already equal. Yeah, we have to plus 1 in order to have the opportunity to get minimum length 1, length 2. So yeah, so this is going to be this. If it's else, then we say high equals mid. Go down. And we keep going, we return low minus 1. Okay, so this is solution 3. Run it. Pass. Alright, check how fast this one is. Submit. I got 3,000 in general. Oh my god. Very, very fast. So, so O log min n1, n2, right? And times what? What's the case of this? Well, that's m. Wait, this one is O n1, right? O n1, O n1, O n2, and then that's gonna be the, well, depending on which one is longer, right? Which one is longer? So because this is, I think we can say it's the maximum of n1 and n2, right? That's the, wait, what's the time complexity? I don't know. I got a bit confused with the time complexity. M plus n, okay, m plus n times minimum mn. I mean, how do you know it's minimum? Times log min. I think it's, alright, this is m plus n, yeah. But this one, it depends. It depends. I mean, we don't know unless we do a check. Check which one is longer. Well, we can. We can do a check. I mean, it's fine. We can do a check. And then after check, to see which one is long. Yeah, let's do a check. So I'm gonna go run through the, let's say if len set1 is smaller than len set2, right? Then I'll return this. Let's keep the cheeky one. So if actually this is len set2 and set1, then we run through set, else any s1 in set2 for s1 in set1, right? So pass. So this will give us n1 plus n2, right? Plus, actually, n1 plus n2 plus the minimum of n1, 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 and n2. I feel still different from what this is saying. This is like multiply. Why is it multiply? The check, right? I mean, these are m1, m2, n1, n2, and then this, right? For eyeing this, I mean, length. Oh, length is increasing, so that has to take into consideration because that's m1, right? We have to go through every one, and each one has a length. Each one has a length. So we can say times length, and next one times length, next one times length, and then we can take this one out, right? This one out, and now the length add together, right? The length add together is going to be squared, right? I don't know, man. I think it's weird. This is times minimum. Times minimum. I mean, this is just all. This is minimum this, and then we do this. It says n plus n. Take a look. The complexity of our naive check is OM plus n times length. Hold on. So the complexity of a naive check is m plus n times length. Well, each one we have to do length. So that's m times length, n times length. That's true. That's true. Yeah. As we create the scene string with this, and such thing with this, and our total complexity when performing our check. So like every time we're gonna do length. Every time we're gonna do length. So we add them together. So it'll be length plus another length plus another length. I don't understand what is min mn. Because for each one, right, we do a length. And for the next one, we do another length. And the length, I'm saying the length will add up to the minimum of m and n. Man, complexity is a little bit troublesome to figure out. So each step is length, and the next step length change. Next step length change until we find it. So it's just going to be length plus length plus length, and they're all different lengths. I don't think the length add up to anything. Now we just record the time then. This is very, very fast. We're talking about 116 milliseconds. Lightning fast. Lightning fast. So I'm going to also comment on this one. Converting the original array to string is lightning fast. Makes the binary search solution lightning fast. It is possible because of the constraint on the value in the array 0 to 100. Which allows for very simple mapping to ASCII characters. String operation. Splicing string is much faster than splicing array, and hashing string for set is also faster, much faster than hashing tuple. Therefore, the string version of binary search is fast. Right. Yeah, that's just my understanding of this thing. All right, we have one more solution. I don't know. Do we want to go for this? Rolling hash or binary search for the answer is the same thing, but we'll use a rolling hash to store hashes in our set structure. For some prime p, consider the following function modulo some prime modulus m. Wait, what? Notably, hash. This shows we can get the hash of all I in linear time. We also use the fact that this equals this mod m. For every I larger than this, we'll want to record the hash all the way to I. I minus length plus 1, I minus length plus 2. After, we will truncate the first element to get ready to add next. Check on our work says we have found a match. No, no, no. Whatever thing that this solution is drinking at, I'm not buying it. I am not buying it. It's unnecessarily complicated. Nah, I think the binary search is pretty good. Rolling hash. You want to explain rolling hash? Use a DP. Yeah, DP is easy. Alright, if we have just same thing, it's trying to see if another person explain, I'll be able to understand. If we have common subarray of length mid, then with the binary search on this mid, then that we can have collisions. So when we evaluate hashes, I go through all hashes and carefully check for each pair if we have common substring or not. I don't understand what it's trying to say. If we have common subarray of length mid, then we do binary search on this mid. Note that we can't have collisions. For fixed mid, we need presume probability of collision is small enough, and is always a matter of agreement in these type of approaches. Grabbing carp. I think that is. What does this robbing carp do? I get begin and end. A is the array, A. So I think this is to hash everything. Alright, I think this is to hash everything. So instead of splicing, this is our way of hashing, right? We turn that into a string and then hash the string. This is to hash the actual splice, right? It's actual splice. And we get 2 hash, and then we do this. We get, let's say the product, NA for EL. What hell is EL in D1? Oh, in D1. Length. So we get a check. What does hash do? M is 0. We return 0 and 0. Q is this. And what the heck? I in range N. D times T. Nope, 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 nope. I think it's complicating me. Nope, I'm not going for it. But everybody talk about KMP. The hell? Wait, KMP is different. Oh, KMP I think is different. I remember reading about KMP, but I forgot. Yeah, I remember reading about KMP, but I forgot. That's fine. That's fine. All right, let's just call it a day. If we need to use KMP, we will probably see it. If we need to use rolling hash, actually, I want a rolling hash. Right? That's rolling hash. The hell is rolling hash? Rolling hash, wrapping carp, string search algorithm. Oh. Alright, so yeah, I'll spend some time reading about rolling hash, but I don't want to implement it. That'll be it for today. See you guys tomorrow. Adios.